Hello everyone, welcome to this new lecture on Direct Preference Optimization or DPO. I am Dheeraj Madan, and today we will be looking at a technique which is alternative to RLHF, which goes by the name DPO. So this was proposed in a paper titled "Your Language Model is Secretly a Reward Model." Okay, so it was titled Direct Preference Optimization (DPO). Your language model is secretly a reward model. And this was by authors from Stanford. And yes, so Rafailov et al. I'm just writing. Rafailov is the first author. I'll post a link to the paper in the description box below. So the idea in standard RLHF approach is that once when you're training for a large language model, the first step is of course that you have to train it on unsupervised data. Then conditioned on some input X, you try to train it on supervised data, which is that conditioned on some input X, there is a ground truth response, a generated response Y, and then you train your model to produce that response, right, in an encoder decoder fashion, right? So that could be the next instruction fine-tuning approach, which could be on tasks, for example, like question answering, summarization, conversational tasks, etc. During the RL stage, you basically for each prompt X, you try to produce two possible outputs, Y1 and Y2, which could be sampled from your language model. And then essentially you have human labelers who annotate these responses as which one of these is better. And based on these responses, you first learn a reward model which tries to model these preferences, and later you fine-tune your language model which tries to maximize the expected reward which you have learned. So basically, in the standard RLHF, right, when you're learning from preferences, you do it in two steps. So the first step is to learn a reward model. To mimic preferences, distribution of preferences. And the second step is to learn a policy to maximize the rewards. Right, so we'll study these steps in detail. We'll look at these steps in detail as well. But essentially, this is a two-step approach. The idea in DPO is that, well, given a reward model, there is a closed form solution for the optimal policy, and using that you can invert that to given a policy, you can derive an appropriate reward model. So you can have a closed form relationship, or a one-to-one mapping between rewards and policies. And while learning reward model itself, you can directly learn the optimal policy using that closed form relationship. So I'll just write this high level idea. Okay, we'll study all these steps in detail, but I'll just write the idea in DPO. So the idea is that first we'll derive a closed form expression for optimal policy in terms of reward. And then using this, we'll try to directly learn optimal policy from preference data, right? And how do you do that? Well, if you have a closed form expression for optimal policy in terms of reward, you can get a solution for for reward in terms of optimal policy. And then by substituting that, while directly training the reward, what you do is that you directly learn the policy. We'll see how it works, right? So the high level idea of today's talk is going to be as follows. So firstly, I'll just write down this outline for the lecture. Okay. So first we are going to review the RLHF pipeline. Next, we'll derive the DPO objective using by deriving a closed form solution for optimal policy in terms of reward, and then we'll try to do some basic theoretical analysis on the above. Right, so they are indeed able to show that their techniques works better than standard RLHF for some tasks, which includes summarization as well as question answering. I'll refer you to the original paper for all those experimental details and results. So in today's video, we won't go into too much of experimental details. So let's first begin with a review of this RLHF pipeline. So the first stage in RLHF is to train an unsupervised language model. Right? So these are essentially the steps for general LLM training. RLHF is of course one part, but I'm listing down the full pipeline. Okay. So the first step is to train an unsupervised model. Supervised model or LLM for modeling distributions of a sequence of these tokens which are coming from this distribution pi x. So pi is the unsupervised model which we are learning, unsupervised language model, right? And this can be trained from as large set of sources as possible, which could include data scraped from internet or books, wiki corpus, etc. Right? So you don't need any annotations over here. You just need long chunks of text from which you can learn. So this could be some books corpus, wiki corpus, online like any web scrape data. And in general, you don't need human annotations over here. Maybe a little bit of data cleaning might be required, but then it's not specifically you are not trying to get labeled data from humans in this task. The next step is called supervised fine tuning or instruction fine tuning. So here we fine tune the previous model with high quality data on a task of interest, right? Which could be QA, summarization, etc. So fine tune the previous data. On some task of interest. This could include question answering, summarization, dialogue, right? So here essentially you will need some human annotations. You will need a labeled data, and this is supervised fine tuning. So the amount of data which you have for this task might be much lesser, but of course this is much more high quality data. And here you are learning a sort of a supervised fine tuning model which models the distribution of a response sequence y given an input prompt x. And the third stage, which is RLHF, is what we will focus on right now. And this is the stage which DPO seeks to make faster and more accurate. So essentially, this RLHF or reinforcement learning from human feedback consists of two steps. So first is a reward modeling phase. Okay. So here, we use prompt X to generate pairs of response or responses y1, y2, which are sampled from let's say the supervised fine tuning model y given x. Okay. And human labelers can now annotate these and provide their inputs on which of these is better given the response x. So human labelers can provide their preferences denoted as y win greater than y lose given x. So by win and lose, I mean that I'm indicating the response which is labeled higher as the winning response and the other response is the losing response. So between y1 and y2, one of these is going to be labeled higher than the other one. And the human labelers are, they are not providing any set of scores. They are only comparing these two responses. Okay. And now we train a reward function r phi xy, okay, corresponding to these preferences. Okay. And in order to learn a reward function, what we do is that we need to make some assumption on the probability distribution. So the assumption is that like we assume a preference model, which can, so we assume a probabilistic model for preferences. And one of the commonly used model is the BT model or Bradley-Terry model. Okay. So here this models the distribution that the probability that y1 is a better response than y2 given input x as exponential of r phi xy1 over exponential of r phi xy1 plus exponential of r phi xy2, okay, which is nothing but sigmoid of r phi xy1 minus r phi xy2. How do you show that? Well, you divide both numerator and denominator by exponential of r phi xy1 and you will get 1 over 1 plus exponential of minus of r phi x1 minus r phi x2, which is just sigmoid of r phi x1 minus r phi x2. Right? So essentially this is for, a pair of responses. Now this is the assumption which we are making, right? And these are, the data which we have collected, right? So you like basically you can collect this data for multiple prompts. For each of these prompts, you can generate two responses y1 and y2, and you have human labelers who have annotated these. So from the above, what we are assuming is that we have a static data which is labeled as a sequence of prompts xi's, the winning response ywi's, and the losing response yli's. Okay, and we have, let's say, a bunch of these triplets. Now we train a binary classification loss to minimize the negative log likelihood loss. Okay, so train a binary classification model to minimize the negative log likelihood loss. Right? So essentially, This loss is based on a set of parameters phi, which are parameterizing a reward model and the data. And essentially, what we do is that we compute the negative log likelihood over all these examples which are sampled from our data. Of log probability of YW is greater than YL given X parameterized by phi. So this is nothing but minus the expectation of X YW Y loose sampled from data log of sigmoid of R phi X YW minus R phi X Y loose. Okay. And now how do you choose a network for these reward models? So essentially you can consider the same transformer model as you had for your supervised fine-tuned language model. And in fact, you can even have the same parameters, except that maybe you can add an initial linear layer to produce the reward scores. Okay. So Rxy or R phi xy can be initialized from the same transformer as pi SFT with an additional linear layer. Okay. Next, what we have is an RL fine-tuning phase. So once you have trained a reward model, then you would want to maximize the expected reward, and this is over the policy with which you are training, right? So your policy is essentially the language model. So here we are going to fine-tune the language model to maximize the train reward function. Right, with the following objective. Okay, so we are going to maximize where the policy is pi theta by given x. Okay, the expectation of x sampled from data, expectation of y sampled from pi theta by given x, the reward function r phi xy. Okay, so we are going to maximize this expected reward where the expectation is over the language model, right? The probability of a sequence y being sampled conditioned on the input x, right? So we are going to maximize over the set of parameters of the language models theta. Okay. But other than maximizing reward, the response, the distribution of response should also satisfy the condition that it's not too far off from the prior distribution. And so we also have a KL divergence term which tries to ensure that the distribution which is being trained is close to the original distribution based on some reference distribution pi ref y given x. Now, so pi ref y given x could be a base or a reference policy which can come, for example, from the initial SFT model, right? So basically the original pi SFT model. So before you begin RLHF, there is a supervised fine-tuned model which you already have, and you can use that as the reference policy. And in fact, even pi theta can be initialized to these parameters. And now we maximize using an RL approach, for example, PPO, right? So PPO is an actor critic method. So essentially, other than these policy parameters, you also have the Q-learning parameters which you are maintaining. So we won't be going into details of PPO today because that's not the focus of this lecture. But essentially, you will need an RL approach, right? And PPO is one of the examples. So you can train using an RL approach. Example, PPO. And now the key insight of DPO is that we can get a closed form expression for optimal policy in terms of reward. Okay. So essentially we'll try to find an optimal pi theta y given x for each x. Okay. So find an optimal pi theta y given x for each x. Right. So of course, so we have already discussed this RLHF pipeline. So now we are trying to derive the DPO approach. So the key insight which I also discussed at the first part of the lecture was that we'll try to derive a closed form expression for optimal policy in terms of reward. So how do we do that? So let's try to solve for the optimal policy pi theta y given x for a given input x. So for a given input x, we are trying to maximize the set of policies pi theta y given x. Okay, the expectation of y sampled from pi theta y given x r phi xy minus the beta times the KL divergence between pi theta y given x and pi ref y given x. So this was how we formulated. And the idea is that this KL divergence is also an expectation over y sampled from pi theta y given x, of which quantity of log of pi theta y given x over pi ref y given x. So we can write it as maximization over pi theta y given x, expectation of y sampled from pi theta y given x, of which quantity r phi xy minus beta times log of pi theta y given x over pi ref y given x. Okay, and now what is this quantity? Right, because KL divergence is also expectation over pi theta y given x log of pi theta y given x over pi ref y given x, and now we have to maximize. So the key insight is that we'll try to express this entire expression as KL divergence between two distributions. And what are these distributions? We'll try to come to that just now. And in order to do that, so it's already in expectation. How about expressing this term as a ratio of logs? So can we do that? So in order to do that, first try to remove this minus beta, and we can take this minus beta outside the expectation, and we'll also have to adjust for that in the R5 part. So let's do that. So I'll take minus beta out. Right? So expectation is linear. We are using that assumption already. So this is y sample from pi theta y given x, and this R5 term, it will turn to minus R5 xy over beta, and then this is plus of log pi theta y given x over pi ref y given x. So I have taken out minus beta from this whole expression, common out, and I have also taken it outside the expectation by linearity of expectation. And what am I left with now? So I am left with log of pi theta y given x over pi ref y given x. Okay. And now I want to express this entire expression as a ratio of logs. So let's do that. Before that, we see that there is a maximization of minus beta times this quantity. So this is equivalent to minimizing this is equivalent to minus beta times the minimum over pi theta y given x, expectation of y sampled from pi theta y given x, and here I have minus r5 xy over beta plus log of pi theta y given x over pi ref y given x. Right, so when minus beta goes outside maximization, it becomes a minimization problem. The reason being that beta is positive, so minus beta is negative. And essentially, the thing is that the lower this quantity is, the larger is minus beta times this quantity, right? So if I have to maximize minus beta times an expression, I'll have to first minimize that expression so that minus beta times that expression becomes high. Okay. And now it seems to look like a KL divergence, except that I'll have to first express this as a ratio of logs. So how do I do that? Well, I can write minus r5 xy over beta as exponential of, so I'm going to throw away this minus beta. It's just a scaling factor, and anyways my goal is to find the optimal set of parameters for pi theta, right? The actual optimal value does not matter to me. The parameters which achieve that value for pi theta, those matter to me. So I can write it as minimization of pi theta y given x, expectation of y coming from the distribution pi theta y given x. Okay, and here I have exponential of minus r5 xy over beta plus log of pi theta y given x over pi ref y given x. Okay, what I meant to do was that write it as a log, right? And that's why I introduced this exponentiation. This is log of exponentiation of minus r5 xy over beta, right? And now it's a sum of logs, so I can combine them together. So overall what I have is minimization over pi theta y given x, the expectation of y coming from pi theta y given x, and then I have log of pi theta y given x over exponential of r5 xy over beta times pi ref y given x. Okay. Now question, is this a KL divergence? Think about it. Well, the answer is almost but not fully. Okay. Why is it so? because it is not normalized, right? Because the denominator is not normalized. So what should we do? Let's normalize the denominator, right? Because see, numerator we have a distribution pi theta y given x. In denominator we have exponential of r phi xy over beta times pi ref y given x. So is this a distribution? May not be, right? Most likely it is not. So what do we do is that we multiply and divide the denominator by a normalizing factor. So we multiply and divide the denominator by zx, which equals sum over y pi theta y given x exponential of r phi xy over beta. So what is the expression which is left now? The expression is minimization of over pi theta y given x, expectation of pi sampled from pi theta y given x, log of pi theta y given x over, okay, in the denominator when I normalize I need to sum over e exponential of r phi xy over beta times pi ref y given x. So there's a typo here. Okay. Pi ref y given x exponential of r phi xy over beta. So this is what I had earlier. Now what I'm doing is that I'm dividing this denominator by zx, which means that I have multiplied the numerator by zx and there is a log outside. So what do? We subtract log of zx to balance this. Okay. Now tell me, is this a KL divergence? Right? So there is a minus log zx term as well. But since this is minimization over pi theta and zx does not have any theta parameters, so what I can do is that I can even ignore this term, right? It will not affect my optimal set of parameters, right? So as before, we are only trying to find arg max or arg min over here. Now does it look like a KL divergence? Well, it's an expectation over pi theta y given x of log of pi theta y given x, which is what I want, over this particular term, right? And this is a valid distribution now. We have already normalized it. So this is indeed a KL divergence, and I can write it as minimization over the distribution pi theta y given x of KL divergence between pi theta y given x and pi ref y given x times exponential of r phi xy over beta. Okay. So over zx. Right? So we have division by zx also in the denominator, right? Only then it becomes a distribution. So what is the closed form result? Do you see from here? So KL divergence between any two quantities, right? Between any two distributions P and Q is always non-negative, and KL distribution being 0, right? When does it occur? So it occurs when P equals Q, right? So that is the, so okay, if P equals to Q. Right? I'm not writing only if, because what we actually need is that Px equals to Qx whenever Px is non-zero, right? So if Px equals to Qx whenever Px is non-zero, then even when Px is 0, then Qx has to be 0, because these are distributions, right? They should sum up to 1. So, but actually there are also some cases, if the measure of the space where Px is not equal to Qx, that is a 0 measure set, then also it's fine. So I'm not going into all those details. But of course, if px equals qx for all x, then we are done, right? So one such closed form solution is that pi theta y given x equals pi ref y given x times exponential of r phi xy over beta over zx. So if these two distributions are equal, then I'm pretty sure that essentially mm, the KL divergence will be 0, which means that it is something which is going to minimize this particular objective function, right? Which is what we also wanted. Now, what our goal was to be able to solve for pi in terms of the reward, and then we can invert this expression to get an expression for reward in terms of optimal policy. We substitute this expression in my original objective in which I was training for rewards using my preference data, and that will give me a valid objective function. So let's do that now. So we invert r phi xy in terms of policy pi theta y given x. So what do we get now? So how do we do that? Well, firstly I take everything to the other side. So what I have is exponential of r phi xy over beta is pi theta y given x times zx over pi ref y given x. Okay. And now I take log on both sides. That will give me r phi xy over beta, which equals log of pi theta y given x, okay, plus log of zx minus log of pi ref y given x. So I can solve for r phi xy as beta times log of zx times pi theta y given x over pi ref y given x. Right? Well, actually, I don't have a full closed form expression because there is a zx term as well, right? And because of this zx term, and actually, like if you look at the zx term, that essentially involves knowing r phi xy as well. So although I'm saying that I'm claiming that I'm writing r phi xy in terms of policy, but then it also involves the zx, which involves r phi xy, right? But essentially, the thing is that zx does not involve any parameters, and as we will see in the objective function, which comes from Bradley BT model. So essentially, this will not matter to us. In the Bradley-Terry model, this zx, this term is going to vanish away. So let's try this now. So this is the reward model in terms of policy and something which depends on x, right? It is not dependent on my parameters. So let's recall the objective function for reward modeling, which came from the Bradley-Terry model. So, okay, so that objective function was minimization over the set of parameters phi, expectation over inputs x, y win, y lose, coming from data set, log sigmoid of r phi x y w minus r phi x y l. Okay, and this is nothing but minimization over phi, expectation over x, y w, y lose, coming from data set D, log of sigmoid of. So right. So basically, if we now write r phi x y w minus r phi x y l, we will have the terms beta log zx pi theta y w given x over pi ref y w given x minus beta log of zx pi theta y lose given x over pi ref y lose given x. And now if you see, this zx term will get cancelled because this is log of zx plus log of the remaining quantity. This is also log of zx plus log of the remaining quantity. So I can actually cancel away log zx. So even though I don't know the zx, for that I needed to know the reward, but I can just cancel this away. And now when I'm minimizing it, essentially, I was minimizing over the parameters of reward, but now these parameters of reward have been directly expressed in terms of the policy. So essentially, the objective function boils down to minimizing over the set of policies pi theta y given x. Actually, I should have substituted here only. So when I'm substituting rewards in terms of policy, this minimization over phi changes to minimization over theta. So what do I have here? I have minimization over theta of, there's a negative sign, right? So negative log likelihood is what we minimize. Log likelihood is something we maximize. So minimization over theta, expectation of x, y win, y lose, sampled from my data, log sigmoid of beta times log pi theta y w given x over pi ref y w given x minus beta times log of pi theta y lose given x over pi ref y lose given x. So we minimize over the parameters of our policy network theta this particular quantity, right? And now we don't have to do any reinforcement learning at all. So if you see this expression, this is now a purely supervised learning task from this preference data, right? And now we don't need to do these steps of learning the rewards and then learning the optimal policy. We can directly do it using supervised learning. Okay. And now let's try to analyze this a bit theoretically. So let's try to compute the gradients of this particular loss function which we have defined. So if we take the gradient with respect to theta of this loss, okay, this particular loss which we have over here, okay, so like I will encourage you to actually compute the gradients yourself, but you will find that this equals minus beta times expectation of x, y win, y lose coming from data set, and then there is inside this expectation I have sigmoid of r phi x y lose minus r phi x y win. Okay. This much times the gradient with respect to theta of log of pi theta y w given x minus gradient with respect to theta of log of pi theta y lose given x. Okay. So we have that gradient as the expectation, and this is this quantity sigmoid, right? So this is nothing but the probability that the losing response is better than the winning response given x, and this consists of the difference of gradients between log pi theta y w given x and log pi theta y lose given x. So if I would have formulated the objective as something like maximizing the log likelihood of the ratio of pi theta y w given x over pi theta y lose given x, then I would have just gotten this particular term. but I'm also getting this extra term, which is the probability that the losing sequence is better than the winning sequence given x, and this additional term for each input x is what is trying to scale my objective function, and this is actually giving them an advantage as well, right? So if we would have chosen just to define the loss function as minus log of pi theta y w given x over pi theta y loose given x, then the scaling term would not be there. Term is that for those sequences in which our current model is giving a higher probability to the losing examples, I'm giving more weightage to those terms, right? So essentially that's that's maybe you can take that to be one intuition for this particular sort of DPO algorithm, right? So basically you are doing a gradient updates on this objective function minus log pi theta by w given x over pi theta y given x, except that you are also scaling the terms by the probability that the losing one is giving a higher the probability of losing sequence getting being better than the winning sequence under the model, right? So if this probability is 0, then of course you don't even need to use this example while training, right? So if it is giving higher probability to the winning, let's say in the probability of winning sequence is already 1 for that example, then you can even throw away that example. But if it so happens that that is very less and the other is the losing example is getting higher probability, then we weigh this example more. So that away from this particular model, and apart from DP model, there is a generalization for that to multiple preferences. Let's say instead of y1 y2, I had y1 up to 1k, and I'm using the preference data to rank them. Then essentially even there we can have a softmax sort of distribution over these, and we can again consider the similar objective function, and the DPO framework extends to that as well. So read that in the paper, and in fact you can also read the experimental section. They have shown that for summarization, QA, and some other conversational AI tasks, they're able to do better than standard RLHF. Right? So that's it for today's lecture. I'll post a reference to the original paper as well. I'll post a link to that. So do read that. Thanks and goodbye.